Welcome to the Logic Videos. I'm Scott Aiken. You're you. This is the second video on truth functionality. I'll be introducing the truth functional connectives of conjunction, disjunction, and negation. So, the big idea to start is, again, the idea of truth functional complexity. Again, a truth functionally complex proposition is a complex proposition whose truth value is determined by the truth value of its component propositions. And we showed last time that truth functionally complex propositions are different from non-truth functionally complex propositions by the fact that what you do is you look at the component propositions, you look at their truth value, and then that tells you in a law-bound way what the truth value of the complex is. We started off with the example of and. And so let's now try to have a systematic representation of and. So one of the things to start is that if I say something like A and B, notice that it's possible for, now we'll think every proposition could be true or false. Given the fact that I got two, there are four possibilities. They're both true, one's false, one's true, or they're both false. So let's represent that with what's called a truth table that represents all the possible combinations of true and false versions of its component propositions. So A and B here could be, A could be true, or it could be false. B could be true, or it could be false. And what we do with the truth table is we represent all those possible combinations. First line, one line is alternating T's and F's. The next one is 2 and 2. If we had a third one, it would be 4 and 4, and we just sort of repeat this one. The next one would be 8 and 8, and so on. So the crucial thing to see is that what we have with this truth table is a representation of all of the possible combinations of truth values for the component proposition A and B. So if it's false, if A and B are both false, then the AND claim comes out to be false. If either one of the two components of A and B, if A is false or if B is false, and it doesn't matter if the other one's true, the whole thing comes out to be false. The only way for a claim A and B to be true is for both of them to be true. It's the only way. And so this is the truth table for the truth function called conjunction. And the way that we're going to represent conjunctions is with the following little notation. I'll start putting them over here. It's going to be a little dot between the two of them. A dot B. Okay? So far, so good. And that's actually pretty intuitive. Conjunction, tracks, natural language, and. Okay, that's pretty cool. Let's look at another one. Let's imagine that if I say A or B. Okay, that's different. They're grammatically the same, by the way. They're grammatically very similar, right? They're just two independent clauses stuck together by an or. But semantically, right? So here we're doing something different from grammar. We're looking at the logic of this and the semantics of this. A and an or have a massively different semantic function. Let's look at it. Okay, so again, basic truth table over here. Let's start plugging them in. So if I say A or B, let's say you could get an A in this class by either doing all the homework on time and things like that, or cramming really hard right before the tests. Okay, so those are two ways for you to be able to get to do the class. So the thought here is that if neither is true, then I said something false. Right? If one ends up being a good route to being able to get an A in the class, if cramming is your way, then that's true. Or if keeping up with the homework is your way, that's true. So far, so good. The last thing to see is that it's possible for some or statements to be such that they can both be true. You can get an A in my class by both keeping up with the homework and cramming. So as a consequence, that or claim is true. Now, often in natural language, we will often hear or statements as not including that top line. So one of the crucial things about the way that we're going to be looking at language in this logic is that we're going to be treating or claims as what's called inclusive. Inclusive interpretations of or has it so that or claims make it so that it's possible for both of the or claims to come out as true. Now notice that that's different from exclusive or. Exclusive or has a false at the top, but we're not doing it that way. Okay? We're going to do it this way because at the very least it makes it so that we can treat as many things as true as we can so that we can test it for validity. So we're going to stay with inclusive or. Once we've got this truth table up and running, this is a systematic representation of how we're going to think about or claims. And or claims come in all sorts of shapes and sizes that we'll look at in a little bit, but what we call them for the purposes of this logic is disjunction. And the way that we represent disjunctions as truth functions is with a little caret or a vel. Comes from Latin for or, which by the way was an inclusive or. So that's, again, just the history of this logic sort of shows its semantics with that. So far we've got two connectives, and or, conjunction and disjunction. Notice, by the way, what's important is that what we're going to call the component propositions of these two complexes, so we're going to call them conjuncts and disjuncts, right? So we have a conjunction, a disjunction with conjuncts and disjuncts, respectively. Well, one last one. And the last one is negation, thinking about what it is to say not. So if I have some proposition, so again, just like with our reasoning from the very beginning, she's at the bar or she's at home, she's not at the bar, right? What's important is to say that we've got a picture, right? Now again, think about this in terms of the notion of complex propositions, and in this regard, a truth functionally complex proposition. Claiming that she's not at the bar, what it does is it picks up the picture of your friend at the bar and says, says, no, not that. So it takes that picture and says, not this. And that's what makes it a truth functional complex. It has a proposition and then it has a not on the outside of it, and that makes it truth functionally complex. So if I have not P, if I start off with the claim, there's the component proposition, that proposition could be true or false. So if P is true and I say it's false, I've said something false. And if P is false and I've said that it's not true, then as a consequence I've said something true. What negation is it kind of flips the truth values over from the original truth value. So again, if P is true and I say P is not true, I've said something false. If P is false and I've said that it's not true, I've said something true. So the way that we represent that is with what's called a tilde. In this regard, what I've got are now three truth functional connectives that allow me to be able to represent not just the core base truth values of the component propositions, but also a larger truth function that again is determined in a law-like fashion where you take the base truth values of the components and you then are able to yield a truth value for the complex. We'll look at two more in the next video, conditionals and biconditionals.